What are data structures? Data structures are specialized formats for organizing, storing, and managing data in computers. They provide efficient ways to access and modify data based on specific use cases. The most fundamental data structures include arrays, linked lists, stacks, and queues. Arrays are ordered collections of elements stored at contiguous memory locations. They provide constant time access to elements using indices, but typically have a fixed size. Linked lists are sequences of elements where each element points to the next. They can easily grow or shrink, but require sequential access to elements. Stacks are last in, first out data structures. Elements can only be added or removed from the top, like a stack of plates. They're used in function calls, undo mechanisms, and parsing. Queues are first in, first out data structures. Elements are added at the back and removed from the front, like a line of people. They're used in scheduling, breadth-first searches, and buffers. To summarize, data structures are like specialized containers for organizing data. Each structure has specific efficiency characteristics that make it suitable for different scenarios. Choosing the right data structure depends on your specific operations, and these fundamental structures form the building blocks for more complex ones. Choosing the right data structure is crucial for program efficiency. Selecting the appropriate data structure can dramatically improve program speed, memory efficiency, code readability, and maintainability. For fast random access to elements, arrays are ideal. They provide O1 lookup time but typically have fixed sizes and are inefficient for insertions and deletions, which require ON time. When you need dynamic sizing with efficient insertions and deletions, linked lists work better. They allow for O1 insertions and deletions, but sacrifice random access speed. For searching operations, hash tables offer O1 average time complexity for lookups, insertions, and deletions. They're unordered, but extremely efficient for key-value mappings. Trees are perfect for hierarchical data and maintaining sorted elements. Binary search trees enable O log n search, insertion, and deletion operations when properly balanced. Graphs represent complex relationships between objects. They're ideal for modeling networks, maps, and social connections, with specialized algorithms for different problems. When choosing a data structure, consider what operations you'll perform most frequently. The right choice depends on whether you need fast lookups, insertions, deletions, or traversal capabilities. Also, consider your memory constraints, whether you need ordered data, and implementation complexity. Using the wrong data structure can dramatically impact your program's performance.